live,
Back.
apparently.
Okay, we're being live streamed, are we?
Oh my gosh.
Okay.
Guys, no bad words.
The stream's current bitrate is higher than the recommended bitrate. We recommend you use a
That's
stream
nice.
bitrate of 4500.
No, it's 10. I see it's 1080p.
There we go.
Do you?
So
Is
the
it just
problem doesn't
preview
actually
then?
exist. But you've now got a high bit rate, which is good.
No, it says 10. I'm watching it in
Yeah,
1080p. Everything's
1080 as
fine.
well.
Oh,
Yeah.
okay, cool.
Everything's fine. Cool. Is that
Maybe
all I'm
your
gonna do
monitor resolution can't go higher than 360, Perry. You're rocking out with.
for? No, I'm
Yeah.
getting the
The
same thing in the
RTTV.
preview window. I'm getting the same thing in the preview window. I have no idea why that is.
I presume the preview's downscaled so that you can just like fucking see.
Yeah, but every other
Quite
preview has
possibly.
been completely fine.
So if I refresh the page,
Might be might be fine. I don't know.
yeah, if you refresh the page, Perry, it's fixed. You just have
Ah,
you can then manually
right.
select it.
I presume it's just caching.
If you
it.
press F5, 5 people watching. Is that?
6 concurrent viewers, Harley.
Oh,
Hello,
okay.
2
gamers.
likes.
Oh my days! You're using IDA.
33.
Oh,
likes
no,
and
no.
half
How
just
dare you
shows.
use proper software for this?
No, no, no. Most of it's in Ghidra. This is just open from something else that I was working on. But
Fair enough.
I'll share that.
Cool. So yeah, I will disconnect. I'm glad everything's working. DM me
Security
if
number,
Oh,
so
bye,
we can
Harlan.
take it.
Bye bye, Harlan.
Bye.
See ya.
33 likes and Harlan shows his toes, guys. Remember. Can we get there? Also, if you're from Cardiff, please close the stream.
Card for the...
Can't be having it, man. Can't be backing them.
Ugh. Right. When's best to start this then?
we'll give it a few
Technically,
more
you've
minutes.
already started.
I mean, yeah, but I'll just wait out. Load up the stream.
Go for an audio sync clap, and then off you go.
No pressure.
No pressure, yeah. Right. Right, well, I'll just jump into it then. That's probably the best way.
Yeah, you might as well just get started.
Yeah.
Audio sync clap, and off you go.
What audio sync clap? There you go. I'm going to be talking about malware today, and how to get sort of started looking, analyzing, and just reverse engineering malware basically. So for this talk, I'd recommend you basically get the following: some form of debugger. So my debugger of choice is x64 debug. That is the best one. No other competitors to that. My opinion is the best, obviously. Then for the disassembler decompiler, I'm going to be using Ghidra for this talk, which will have an integrated debugger soon, which is going to be good, so that it'll actually be at the same level, roughly, with IDA Pro, hopefully. There are some other ones, so Binary Ninja or Cutter, which you can use. I've heard good things about Cutter, but every time I've tried to use it, I've not really gotten into it, so I can't personally recommend it, but we'll be using Ghidra today, mainly. Then on the more high-level analysis side, CFF Explorer is sort of a PE file explorer. PEID and PEBEAR are also in that category. They allow us at a high level to view a file, a PE file, which for those unaware are basically what Windows uses as executable files. And they basically give us a high-level overview of the headers of the file and any resources and things of that nature within the file. It makes it a lot easier to get a good overview of what a file itself is actually has within it, essentially. Then on the more dynamic side, sysinternals within sysinternals API monitor, really useful, as well as iNetSim and Wireshark. So iNetSim and Wireshark are for networking. iNetSim will basically simulate any network requests and connections, and it essentially allows us to, whenever malware is connecting outbound, it will simulate that protocol in particular. So, for example, if malware is trying to connect over SSH, it will simulate SSH and respond accordingly, and that allows us to capture traffic that malware sends out of the network. Wireshark does that, but on a more passive scale. It just monitors packets that go in and out. So you can take your pick out of either of those. iNetSim is probably a lot easier to use, but Wireshark will give you a lot more in-depth information about the packets in particular. But that's not really required for malware analysis, to be honest. So some basic Python knowledge, which just for general scripting, very useful to have, especially when scripting within our disassemblers. Ghidra in particular has a really good API system. It can be a bit daunting because basically everything is available to you. But once you learn the basics, it makes it a lot easier to get your head around. And then finally, just your ability to be persistent, really. Like there's going to be a lot of times when you're reverse engineering things where you will not want to carry on or you can't figure something out, but just the ability to keep going, keep like looking at it from a different angle, that will be really useful because eventually you will figure out what's actually going on. So just a quick disclaimer, all the malware that I've written for this talk is non-malicious, so if you do play around with it, it will be fine. Although I'm calling it malware, it's basically just mini little reverse engineering challenges with some malware ideas sprinkled in there, basically. If you do decide to look at real malware, I've provided some links at the end of the PowerPoint for where you can get started and really have a look at different resources, like getting a proper VM set up and things like that. And I'll probably be around after the talk, so you can just ask me about that at the end. And then finally, enjoy. So, what is malware? So malware at its core, it's malicious software, right? Usually, you've got subgenres of malware, essentially. So like botnets, ransomware. More prevalent now is mainly C2 malware, which is essentially like botnets, but a bit more on steroids, essentially. There's a big prevalence of them today, and if you look at probably the top 10 most prevalent pieces of malware that are in the wild, you're going to see the majority of those have some C2 capabilities where they can connect back to a server and receive commands. Most of the malware that you'll ever really look at is going to be quite small and focused on stealth. You're talking like 4 to 10 kilobytes roughly in size. So you're not really going to run into anything that's huge. So it actually makes it quite easy to sort of delve quite deep and really like understand what something's doing in a short period of time. And although this isn't official statistic, it will definitely feel like it if you start looking at proper samples. Like most of them will be written for Windows. macOS has become a lot more prevalent. Not to say that like there's no malware on macOS or Linux. There definitely is. It's just you won't run into it day to day, and a lot of the malware that's out there currently is not as advanced than compared to the Windows side of things. There's also a bit to do with macOS tends to be a lot more secure by default, and Linux tends not to be as popular, so you don't really see them any malware for those as much, at least. So let's talk about the life cycle of common C2 malware. So usually it starts off with some form of initial infection. So we're talking a like Word doc or a spreadsheet that's got some form of macro inside. So essentially what will happen is a phishing email will get sent out, see attached this invoice, and the Word document that'll have the invoice in it will have infected macros usually, which essentially their goal is to drop another payload to the computer that then runs the malware at the end of the day. You can see 0 days. It's a lot less common, but you can see them. Like, for example, Stuxnet initially had the way it would get initial access was through 0 days. There was a Russian state-sponsored malware a few years ago. I can't remember what it's called now, but that used a 0 day within Word to get code execution and then drop the malware that way. So it can be done. Then on the second stage, you've got a stage payload, which is essentially this payload is usually downloaded from the Word document when the Word document connects to a remote server, sorry, I should say. And it has usually an encrypted version of the final payload within it, and it will slowly unpack itself in memory, which is to say it will decrypt itself and then usually inject into either a version of its own process or into a remote process. For example, Notepad, it might inject into. That would a bad example because Notepad will be closed, but it could do something like that, for example. Then once the payload's unpacked in memory, you'll have the final payload, which will essentially just wait for commands from the C2 server and not really do much else. Sometimes it can set up persistent mechanisms and things of that nature, but for the most part, at least C2 malware will just sit and wait for commands, essentially. So this is a diagram of quite a prevalent piece of malware called Emotet, and essentially how it works is you've got your initial phishing email, then a Word document with macros in it. The Word document will spawn PowerShell, and the PowerShell then downloads the version of Emotet from the remote server. This then causes the stager to download. That will basically unpack itself in memory, and once it's unpacked itself, it will set up a persistent mechanism of like a scheduled task, or it'll do a registry key, which is quite a common one. So that way, if the computer gets turned off for whatever reason, Emotet still retains access. What's quite cool in this case, so this diagram actually talks about some of the modules that come from the remote servers once the stage has been uploaded onto the computer. And one of those that's quite interesting is the ability to harvest Outlook emails. So it actually uses the Outlook API, and it will pass the emails between people, and it does some basic natural language processing on those emails to see whether a response should be made or not. And if a response should be made, it will actually send out an infected Word document to other people. So it basically has this like self-propagation mechanism through email, which I think is actually quite like a cool technique, which has been discovered. So talking about Maldocs a bit more in depth, so they are the main access vector for most malware. If you start from ground zero, you will probably more than likely see some form of Maldoc. They are mostly written in VBA because Word macros. That's what you have to use. It's pretty awful having to write VBA and having to read VBA, and no one should have to do it, but something that we've got to suffer through. You can occasionally come across embedded WL or .xml files, which are basically add-ins for Word and Excel. These files are usually embedded into the Word doc or Excel file and are then unpacked by a macro and loaded it in as an add-in. This way, the malware can get native execution pretty quickly without having to do any staging or injection. The only downside to this is it makes the Word document a lot bigger because you're storing an extra file within the Word document with all your malware code in it, essentially. So something quite interesting about Maldocs as well is that they can actually access any of the user mode APIs available to basically any process without having to write native code. So VBA actually can access underlying operating system APIs like any like NT or just before you get to kernel level APIs. What's cool about that is that you can actually see malware that will do advanced process injection, but from a Word document. It's very uncommon, but it can actually be done, which is it's always interesting when you see that. But most commonly, it will just drop some other payload to disk, or and then run that payload directly. That's the usual scenario. If you have a maldoc and you really quickly want to not like worry about it and you just want to get the payload out very quickly, easiest way is to use an online sandbox. So any run's a good one. There's a few others out there. Like I think one's called like Falcon Sandbox. If you just Google like online sandbox, you'll find a bunch out there that are like allow you to basically detonate the maldoc in a secure environment without having to worry, and you're still able to recover the payload once it's been downloaded from the remote server. So I'm going to quickly walk you through one of the maldoc payloads that I created as one of the challenges, just so you can kind of understand the idea a bit more of what you'll commonly see with these maldocs. So if I go here, documents, and you might be able to see that here you've got this flag. When I opened it, you might have seen that it was running PowerShell. That was due to the fact that I already have macros enabled. If you open this, then you'll probably see a warning banner saying macros need to be enabled or something of that nature. So the first step whenever we've got a document like this is we want to enable the developer tab, which can be done through file, options, and then customize ribbon, I think. Yeah, so customize ribbon and then enable this developer tab. So once we've got the developer tab, we click Visual Basic, and if you see here, we have this this window with our code in it of the macro. So this has an auto open macro. What's special about this is that this will run whenever the Word document's opened, but it has to be the case that macros are enabled for that document for them to run in the first place. So we actually see there's some form of PowerShell here command with some encoded data. Then there's just some numbers being added, but they don't look that interesting. A object's created, a shell object, then that's stored in there, that's executed, and from the looks of it, it's basically executing this command here in a shell object. So it's going to basically execute this PowerShell and then store the result and print it in a message box. So if we very quickly take a look at this PowerShell, we can just do, if we open up Chrome, and then we do cybershell. Once that loads, we can paste in our PowerShell. Just delete the first bit. So from base64, you see we've got what looks like text to find and replace. We want to find dots. Oh, why is that not working? Hold on. Simple dots. Then replace with nothing. Why is that not matching? I'm really not sure why that's not matching. That is very strange. Anyway, I'm not sure why that is, but you can get the general idea. That it's basically assigning a variable, and it's calling this convert to secure string, and it's got a string in quotes, and then it seems to convert it to, once it's converted it to the secure string, it seems to convert it from a secure string and then writes the result of that out. So we can assume from that that this string then is the flag but encrypted that we saw initially. So if I just rerun the macro here, see that PowerShell starts, and then once PowerShell starts, we get this encrypted output. So we can assume that that string then in there is basically our encrypted data, or data that gets encrypted. That was just sort of a quick rundown of what you'll most likely see when analyzing maldocs, because most commonly it spawns some PowerShell, and then that PowerShell goes on to download a payload from a remote server, basically. Right. Back on there. Done. So, unpacking payloads. What actually is it to, when I say unpacking? It's basically you're starting with a payload that's encrypted, and it gets decrypted in memory, and in some form or another is either injected into the current process that you're running in, or it's injected into a remote process. So a common thing that malware used to do was it would inject into LSASS, but now it's less common because there's a lot more security mechanisms in place to stop people from injecting out into LSASS. The reason is because LSASS actually stores all passwords for Windows, essentially. So the for a malware operator, it wants to inject into a process that isn't going to get killed for no reason. It wants to basically, the most likely place for it to inject into at the moment is back into its own code and overwrite the code that's in place at that current point in time. That's essentially a technique called process hollowing in itself. So if your binary is packed, there's a few ways you can actually figure that out. Yeah, you'll notice that it'll have not a lot of imports. It'll usually have like virtual alloc and a few others, but no more than about 10 imports. Another good way of seeing whether it's been packed is if you load it, sorry, I should repeat myself. If there's a resource in there and the resource has a high entropy level, so there's a tool called PE Studio which can show you the entropy of all the different resources within a binary. and I'll show you like a packed sample, so you can sort of understand like what's going on. But if it's got a high entropy, you usually know that that's encrypted in some way. So that's probably going to be loaded and then decrypted at runtime, essentially. So there's actually a few ways this can be automated. There's a group out there called Reverse Engineering Labs or Reversing Labs. I'm not entirely sure. I can't really remember their name, but they created a thing called Titan Engine, which is a debugging engine, and that can be used to automate this unpacking process, because usually what happens is there's a few common calls that are made when the unpacking process is being done. There's another site called unpack.me, which unpack.me. It will create common signatures for packers, and it will basically create unpackers for those. There's a general technique which I'll show you in a sec for how you can start with a packed binary and how you can unpack the actual data from it. It's just a bit repetitive and it's a bit of a pain usually. So I would actually recommend just using an automated service for something like this. You don't actually really gain much from the reversing process of the packed payload, because you actually want to kind of get to the malware itself. So let's do a quick demo of unpacking, and I can show you a bit of x64 debug as well in the process. So if we close that. So I'm going to use one of the, I think what's the best thing to use for this. So if we open up P Studio, and I'll show you one of these things should be packed here. I'm not entirely sure which one. I should probably organize my desktop a bit more, but if we drop that into P Studio, I think that was packed. You see this actually does quite a lot of things to our binary, and it gives us quite a high level overview of the PE file itself. So it gives us, it scans it with VirusTotal first. So this is an email attack sample, and as you can see, quite a few AV engines have detected it as some form of banking Trojan. There you see backdoor email attack, so it is being detected. So we want to look at our resources. This has no resources, so this isn't actually the packed version. This is the unpacked version. That's not very good. Let me try that again. We'll use this version of the challenge because I know this has a resource because I created it. So, so this has one resource. This challenge 2 bin here, which is part of the challenge itself, and you'll see why in a second. But if we move over to the entropy here, usually you'll end up with an entropy that's quite high with encrypted data. So the max is 8. You'll probably end up with something that's like 6.5 to in the range between 6.5 and 8. If it's anything above 6.5, you usually can look into that because that's quite weird. Not many things have that high an entropy unless they're encrypted. So in this case, our string isn't actually encrypted, but this is more just to demonstrate the purpose of the actual unpacking process and what happens when something's unpacked. So if we have a look, you also see here as well, in terms of imports, it tells you what's actually being imported and what's being used. And you see there's actually not a lot of Windows imports in here, which is another good sign that it's actually doing something quite shady, although it's trying to look legitimate. So if we actually open that in our debugger, so that's running. So here's our debugging window. let me just give you a quick walkthrough of x64 debug. So here is all of our registers that we can see. Quite useful, gives us quite a lot of information. We've got our stack here. Here's a more in-depth view of our stack. So we can actually scroll for quite a bit more than what we're able to here. These are dumps, so you're able to just see regions of memory. They're very useful for what we're about to do in a second, because they allow us to basically track a region of memory when it's been allocated, and we can see what's written to that region. So what commonly happens is a executable is decrypted and then it's written to an allocated region of memory. So if we go to, where do I want to go to? So breakpoints. So by default, we have a entry point, a breakpoint on our entry point. So if we run, we're actually in our code now, the code that's been written by the malware author. And then you'll see here that I've already got 2 breakpoints set. So one's on virtual alloc and one's on virtual alloc ex. So those are basically the ones that you want to set. So the way you do that is by doing bp and then virtual alloc and bp virtual alloc ex. And what those Win API functions do is they essentially allocate a region of memory for you to use of a certain size. It's usually used to allocate memory in a separate process. So you can basically open a handle and allocate a region of memory in a process that isn't your own. This is really useful if you're doing any injection of any kind, which I'll talk about a bit more later on. But for now, just know that it essentially works like malloc in Linux. So that's the best way of thinking about it. So if we then run that, so you see that we hit the breakpoint to virtual alloc. If we then return, execute till return here, and we can see that EAX is actually now containing the memory address that's just been allocated. So we can follow that in the dump. And you see at the moment, it's just empty space. So if we just step over, step, right, and then you see this flag gets written into this buffer, basically. So that's just to sort of simulate how shellcode would work and what would happen once the binary was unpacked. Essentially, the PE file would be placed into a buffer for further further modification, further execution. It would basically be placed in there, and then it would be then executed, essentially. So looking at Ghidra, it's a reverse engineering suite, and it was developed by the NSA. It was built for IoT, but it's become quite promising with malware analysis because it's got very, very good Windows definitions, which means that it's fairly easy to reverse engineer even somewhat complex files with. It's not as intuitive as IDA is, and I'd prefer IDA, but it's free and it doesn't cost 5k, so you get open source code with that as well. So you know it's a win, really. It does also have a decompiler, and it's basically at the same level as IDA's, which is very, very impressive, considering up until Ghidra there was literally nothing that was even close to that level. So I just thought that I'd walk through just a basic introduction to Ghidra, and for anyone that hasn't used it, so they can get a good idea of how to start reversing with it. So if we just jump into Ghidra here, so the main window here, this is our project window. This is where all of our files for our specific projects are stored. It has this idea of like a hierarchy. So here I'm in this malware basics folder. That has the source. It's not the source. It has the executable that we just looked at in the debugger within it. And then I'm gonna go to file, import file, and I'm gonna import this Ghidra basics file. Click OK. Ghidra will do some parsing and things like that to it. Click OK. So then if I jump over to my actual Ghidra window, we can open the file. It'll ask us if we want to analyze it. Click yes, and then I tend to enable this Windows P propagate external analysis as well, because it does give you somewhat better results than if you leave it off, so you may as well enable it. Analyze, wait for it to do its thing. It'll probably take a sec. There we go. So it's just complaining that it can't find a PDB, which is where debugging symbols are stored. But it's not going to be able to find it because it's not included with the binary. So if we open up our functions window and then scroll down, you see that we've got a entry function. So looking at this entry function, it kind of looks completely random, and we can't really make heads or tails of this. So what this actually is the entry point that sets up everything before main is called. So in a PE file, this is actually what you find. It's it essentially will set up our arguments and pass them through to main once it's done all of that. Because there's a quick way to find main. So the way you do it is you scroll down to the bottom, and there should be some variable assigned to this unaf ESI. So this is the quickest way to find it. You know that that's then going to be the main function if it's assigned to that, because this is what returns, or this is what our exit code is, sorry. And it does return down here as well. So we can actually very quickly rename that to main. And if we jump into that function, this looks a bit more manageable. We see that it's calling some Windows APIs, process heap alloc, and then it's calling this function down here, which we're not sure what that does. So I can tell you now that when you run this file, what it basically does is it prints out a random address, but we don't know entirely what the address is or where it's coming from. So we're going to walk through what this is doing and figure out what this address is printing. And through the process of doing that, we should be able to understand Ghidra a bit better and be able to do our own analysis from that, essentially. So we just quickly edit our function signature. This isn't necessarily required, but I'd like to do it. So main always returns an integer. Here it just returns 0. So we've got this get module handle W, which gets a handle to kernel32.dll. What this function does is essentially it will return the address of kernel32 and then store it in this variable. So you see that Ghidra has actually correctly typed what this phvar would be, which is a H module. So if we just call this kern32, let me know what that is. So we've got some bytes and flag here and then heap. So you can see that this is allocating some space on the heap and then assigning it to this puvar2. So this looks to me like some form of structure. The reason why I'm assuming that is because it's allocating some heap space and then it's assigning values to that heap space. That's quite strange to do. Usually there's no like array definition for that, so that looks like it's basically creating space to store a structure to me. So if we basically right click on that variable and then click auto create structure, you see that what Ghidra actually does is it'll create a structure for us called astruct, and then casts this heap alloc call to this astruct. Then this actually becomes a lot more clear as to what's going on here. You can see that there's actual assignments being made here. So this field 0 is equal to 5, field 8 is equal to 2000, and field 4 is equal to 1337. So that's interesting. So moving down a bit further, we see that references to kernel 32 are still used in this function. And it's also something in kernel 32 plus this initial ivar here, which is set to another kernel 32 offset, is equal to it. Basically print out whatever these offsets are plus 1337 as our address. So we know whatever it's printing out something to do with kernel 32 plus 1337. So we can assume that this is some form of print function because we know that it does actually print out some data. So if we look at this dat here, which is like a global variable, you see that we've got a 0x and a percent and then an x, which for those who know printf will know that's printing 0x percent x. That's a format specifier for text data. So if we right click on that and retype the global, we can retype it as a chart, see if that fixes it. So that actually does, that looks a lot better now. So we know that this is going to be some form of printf, and Ghidra just hasn't discovered that yet. So we just have to figure out now what's actually going on with this kernel 32 stuff. So it's something to do with it. Now, I said that it returns, this function returns the address in memory of where it is currently. But that also means that it basically returns the start of the file loaded into memory. So if we actually retype this variable as a, oh, sorry, that's the wrong one. If we retype the variable as a DOS image header, which is it PDOS image header? Watch me have to look this up now. Image underscore DOS header. Oh, this is no good. Search that. There we go. Image underscore DOS header. That was right. Yeah. Okay, so let me try retyping that again. Oh, God. There we go. So it eventually did do it. It just needed to be a pointer. That was me just being a bit stupid. But we can see now that this kern32 is actually pointing to this ELFA new variable. So for those that aren't aware, the image DOS header is essentially a struct that's predefined by Windows, and it allows you to essentially pass a PE file. So because it returns the address in memory of where the PE file is stored, if we actually treat it as if it is a PE file, we can actually get a lot of data about it. So here it's pointing to the NT header from our PE file. So if I just very quickly, if I get a picture of the PE file format header, just to make it a bit clearer as to what's going on, because if you're looking at this for the first time, you might be a bit like, what? So if we look at this here, so we see at the top here, we actually have this signature, and then we got the DOS header, and at hex 3C, we have a pointer to the PE header. And that's essentially what we've just found there in Ghidra. We've actually found that this ELFA new is actually the pointer to our actual PE header, which is all this stuff down here, with all these extra bits and pieces in, essentially. So if we go back to Ghidra, and then we can rename this actually to DOS header, because we know what that is now. So this is going to be our PE header. So it's actually called our NT header, but I'm not entirely sure of the proper name for it. So let me just search for it down here. There we go. It was image_NT headers. So image_NT headers. And then you see that Ghidra is sort of auto-completed for us there a bit. So come on, Ghidra. I literally just searched for it. Why? Okay, that's weird. NT. Yeah. Okay, that's strange. I guess it's got to be 32-bit, but image_NT headers 32. So this is now pointing to our DOS header plus dres10 plus dvar1. This isn't actually as clear as what it should be. Let's just try. I don't think that's the correct. I think it should still be image_NT headers. That's still not updating as nice as I wanted it to, but hey ho, we gotta figure it out. So eres2, if we actually look at what that is, as the DOS header, eres. Having a quick Google, we find here that it's somewhere in these reserved words, but it's before our pointer to this new part. So I think this is a good example of actually seeing Ghidra get quite confused by what's going on. But essentially what it's trying to do is add the DOS header plus the NT header here, that we've just created, that we've just found, and it's trying to add the offset that's actually being put here, but it's not doing it properly, which is quite annoying. So what it should actually be doing is it should be pointing to our address of the entry point, but our decompiler has actually let us down massively there. That's really annoying. I will try and figure out why that's not worked properly after this talk, but I'm not entirely sure at the moment. But essentially what it should be doing is it should be pointing to our entry point and then adding 1337 onto it. So that's where the number actually comes from. But I'm going to have to look through the assembly to figure out where it's gone wrong and work out some offsets. And I don't think people should have to sit through that and suffer through that while I do that. So I'll just go back to the presentation with that one. If we jump into it. So let's talk about process injection as one of the techniques that malware has. So the general idea is that you can take code from your malware process and put it into a legitimate process. There's a multitude of reasons why you'd want to do this. So one of them would be to make yourself as malware look more legitimate, because if you, for example, can inject code into the antivirus process, then the antivirus isn't going to try and scan itself. It will just carry on running as normal and just assume that anything that's going on from the antivirus is just legitimate traffic. The same could be said for example, injecting code into Google Chrome if you're a C2 malware, because you're going to be connecting to the internet a lot, and it would just look very suspicious if this random executable is connecting to the internet loads and isn't as an internet-based device or internet-based application. So there's a bunch of different reasons why malware would want to inject. So how does it actually do it? So the main way that it works is virtual alloc is called, which is what we saw earlier. Then write process memory is used, which essentially allows you to do what virtual alloc does of allocating memory, but actually copy the memory into that allocated space. So think about it as memcopy, but you can copy between processes rather than copying from one buffer to another within your own memory space. It can copy to other memory spaces. And then finally, the function called create remote thread is usually called, and what this will do is, it's pretty self-explanatory. It will spawn a remote thread on the in the remote process with the shellcode or the injected code as the entry point for that process, basically. So once malware is on a system, it needs to figure out a way of being able to stay on the system indefinitely, because if it just runs in memory, if the computer gets turned off, then it will lose connection to that machine. So the most common ways that malware is stored within a computer is usually within the registry. This allows it to stay somewhat fileless without having to write to disk too much. I mean, obviously the registry is still part of this, but usually fileless malware comes under the category of writing to the registry. Scheduled tasks is another good way. So on boot, services again kind of comes under the same banner as scheduled tasks. A really interesting technique that I've seen is that the malware will install itself as a Word add-in, so that once Word is started, it will start the malware, even without any like macro enables or anything like that. It basically is, for all intents and purposes, running as part of Word. Some circumstances you can see a technique called DLL hijacking, which is essentially where a DLL is a legitimate DLL is removed and our malicious DLL is placed there instead. So, for example, Notepad will call kernel32, which has a bunch of useful functions for the Windows API. You wouldn't want to do this, but it would in theory work. You could replace kernel32 with your own version of kernel32. But you have one extra malicious function in there, but everything else is the same. And that would then start the malware with any process that calls kernel32. It's a bit overboard, but it can be done in some situations. So we've not really talked about cryptography inside malware. It's quite common that you'll see some form of crypto used. On the basic end, you'll see basically simple XOR encryption methods. On more advanced malware, usually you'll see schemes like AES implemented in native code, which is quite useful to spot. If you can see, the best way is usually looking for the instantiation of an S box, which is what AES uses to encrypt with. Basically, RC4 is the predecessor of AES, so the say it uses the same technique of instantiating an S box. So you can actually, if you can spot those things, it will make your life a lot easier, essentially. You can also see RSA used in malware. Usually, the situation that I see RSA used is to encrypt data that's then sent to the server, and sometimes it will encrypt an AES key with the RSA key, send that to the server, and then the rest of the communication is done over AES. So it's like a sort of simple key exchange system, which is a bit more advanced, but you can actually see it in a lot of prevalent malware. So Emotet's a good example of that. Obviously, if you're dealing with any ransomware, you're going to run into cryptography way more than most malware analysts do. It's usually quite complicated schemes. Even if they're not cryptographically sound, they'll just be made to make your life a lot more difficult, basically. So I kind of touched on this previously with the Emotet key exchange, but malware does, especially C2 malware, it needs a way of communicating. So the most common way of doing that now is over HTTP. It usually implements its own form of encryption. It doesn't tend to adhere to HTTPS. So you will need to go in and figure out what form of encryption it's using to communicate to the remote server. The malware itself, you can actually see this at a high level if it is communicating with a remote server. There's tools like Process Hacker, which will show you network connections and outbound network connections at least, and what process is making that connection. So it's quite easy to see if malware is connecting out to a remote server pretty quickly. And once you've identified that, it's just a case of trying to identify what data is actually being sent across the wire, essentially. So I'm going to cover a few sort of obfuscation techniques, and then I think I'll probably finish off the presentation. So the main three that I want to talk about are string encryption, anti-debugging techniques, and import hiding. So string encryption, you'll see basically in most malware. Sometimes you can see it in the final payload after it's been hacked even, so you will have to figure out what actual encryption method is it using. It usually doesn't use anything complicated like AES, so it's not the end of the world. It's usually just something quite simple like XOR. And the best way to start looking for whether you have encrypted strings is to look for like functions that will definitely take strings as input. So a good example is WinHTTP will take in a URL as an input. That needs to be a string at some point. So if you see that what looks like garbled data is being passed into the WinHTTP function, you know that it's probably encrypted in some way, and then you can cross-reference that to find the string encryption function. If you want to cheat, you can basically run the binary and let it decrypt all the strings at runtime, because it will have to decrypt everything eventually to pass it through. And usually malware authors are quite lazy. They're not going to re-encrypt the strings once they've decrypted them. So once you've let it run for a while, you can basically just dump the binary back onto disk from memory, and then that'll let you see all of the strings decrypted. But it will be very useful for you to actually just try and understand how the string extraction process works and how you can actually get strings from like actually automatically get the strings out of IDA and Ghidra and decrypt them basically. Especially if you run into newer samples which still use the same encryption mechanism, you want to be able to decrypt them automatically. So moving on to anti-debugging. So in simple malware, it will call is debugger present, which is a Windows API that essentially tells you whether your process is being currently debugged or not. If it's set, the quickest way to get around it is to just put a breakpoint on the function and set EAX to 0 once you're about to return. Sometimes you can find that actually that doesn't work and your malware's still crashing while you're debugging, which is usually a sign that they've implemented something a bit more custom. That will take time to reverse engineer and you will have to figure out what's going on. But a quick way of getting around it is to basically you need to manually hide yourself from the PEB. The PEB is like a runtime block of information about the current process. So it stores things like where the different libraries are loaded at runtime. So for example, where's NTDLL loaded, where's kernel 32 loaded. But it also stores like the location of this being debugged flag. And what this does is tells the current process, like, does it have some form of debugger attached to it, basically. It's a lot less hassle now than what it used to be, because x64 debug actually has a setting to hide itself from this like actual mechanism. So I'll just actually quickly show you that as well. So if you actually jump into x64 debug, you see it's got this advanced section here in debug, and it's got this option to hide the debugger, and you see next to it it's got PEB. That's just that will actually hide the current debugging process from the it will basically set the field in the PEB to 0 rather than 1 when it's being debugged. So I've just got a screenshot here to show you what some of the fields look like in the PEB. You can go through and do this yourself with any process. You just need a tool called WinDebug installed, and you basically run this command here, dt_peb at $peb, and then that will print out the PEB for the current process. And you see here at 0x002, at that offset, we have being debugged, and that's set to 1 at the moment, but you can change it yourself, basically, using that technique. So, finally, looking at import hiding. So the idea behind import hiding is that commonly abused API calls are hidden from the analyst by dynamically importing them at runtime. So there's two functions that are used for this, get module handle and get proc address. If you see those two are imported and you don't really have that many other imports, you can assume that what's happened is that there's been dynamic imports done at runtime. It makes your life a bit more difficult, but not much more difficult. You basically just have to set function definitions in Ghidra and it will do the rest for you, essentially. In extreme cases, it can actually be done without touching get module handle and get proc address. And the way that works is it will implement the two functions manually using the PEB as seen before. And it will basically manually parse the library list, and then out of the library list it will parse the exports available, and it will find the addresses for those in memory. But that's a bit more complicated, and you probably won't run into that very often. So I wouldn't worry about that too much. But that basically concludes everything that I've got to talk about. I'll be available for like the next half an hour or so. So if anyone wants to like message me, I mean, anyone can message me throughout on Discord or whatever. So yeah, I think that's everything really, to be honest. So yeah.